This is an answer key to the STAT 2401 final exam review. I noticed some of you were struggling with some of the problems, so I want to work through them for you. So, scenario one says use the mini-tab data, and you're given the link to answer the following questions about the test for normality. And those, of course, are in D2L. But basically, you're going to run a hypothesis test to determine if the data is a normal distribution. Okay, so give me just a second. I'm going to have to save this. I'm going to save it on my desktop. And then I'll have to close it and go back into it because it doesn't recognize my tablet. Okay, now it does. Okay, so the first thing that we initially do in terms of the normality test is it is a hypothesis test, so we're going to state our hypothesis. Okay, so H sub O says the variable, which in this case, the variable is debt, follows a normal distribution. Your hypothesis is written in words, but remember that the null hypothesis must always imply in some way that it's equal or the same. So the fact that it follows would be the case there. Then our alternative hypothesis would imply not equal. So we say the variable, which is the debt, does not follow a normal distribution. And if you'll recall, to run this test, we use the Anderson-Darling value. So I'm going to go out to Minitab and calculate that particular value. Okay, so I'm going over to Minitab. I've already downloaded the data set to my desktop and then I pulled it into Minitab. I noticed that debt is column 7. So we go to Stat, and then I'm going to go to Basic Statistics, and I have to scroll down to Normality Test. My variable is debt. We're doing Anderson-Darling, and then I'm going to click OK. Now, we do get lots of information. We get our probability plot, and off to the right-hand side here, we get our Anderson-Darling test statistic, which is 3.211. Okay, so I'm going to record my Anderson-Darling. Which is 3.211. I also need the p-value, which it tells me that my p-value is less than 0.005. Okay, so the corresponding p-value for Anderson-Darling is really less than, but we'll say it's 0.005. We're then going to compare that p-value that we just found to the alpha, which I believe the level of significance given in the problem was 0.05, but let's double check. Use a 0.05 level of significance. Okay, so we're going to compare 0.005 to 0.05. I've always encouraged you to do this digit for digit. So I have 0 compared to 0, 0 compared to 5, 0 is less than or equal to 5, so P is less than or equal to alpha. When P is less than or equal to alpha, we reject the null. If we reject the null, that means that our null hypothesis is false or wrong. Okay? So because we reject the null, our null hypothesis is false or wrong. And by default, then, the alternative is true or correct. So in this case, the preliminary analysis indicates the variable does not follow a normal distribution. Preliminary analysis indicates the variable, which is debt, does not follow a normal distribution. Then we move on to scenario 2. One of the things that you're going to have to be able to do on the test is to recognize which test you need to do. Should you do a 1 mean z, a 2 mean z, are you doing a 2 proportion, are you doing chi-square, are you doing Anova? So you have to be able to recognize that. And so a lot of it is in the reading of the problem and paying attention to some of the key words. So, for example, scenario 2 says a survey claims that the average cost, of a hotel room in Atlanta is $69.23. To test the claim, a researcher selects a sample of 30 hotel rooms and finds the average cost is $68.43. Assume the population standard deviation of $3.72. At a 0.05 significance level, is there enough evidence to reject the claim that the average cost of a hotel room in Atlanta is $69.23? Okay, throughout this problem, if you'll notice, it talks, first of all, it starts out with talking about the average. And again, at the end, it talks about the average. So average is a synonym used oftentimes for mean. So I know this is talking about the mean. And I also know I only have one of them given. So I have a 1 mean. And I also noticed as I was reading that in about the third sentence, it says, assume the population standard deviation of $3.72. The fact that I know the population standard deviation is my big clue that I'm going to do a Z test. It's a Z test because, again, throughout the problem, as you're reading it, it says claims, reject the claim, test the claim. Okay, so we're testing a claim, which requires us to conduct a hypothesis test. The first step in any hypothesis test is to state the null hypothesis and the alternative hypothesis. And again, your null hypothesis must always and forever contain equal. So my claim is that the average cost of a hotel room in Atlanta is $69.23. So is, it mathematically would imply equal Therefore, this statement is the null. So the mean is $69.23. I convert that sentence that's in words to symbols. We know that the alternative hypothesis is the exact opposite, so the mean does not equal $69.23. Before I go to calculate my test statistic, I like to identify all of the information that I need. For a one mean z-test, we need the population mean, the population standard deviation, the sample mean, the sample size, and my level of significance. My population mean comes from the hypothesis, which is $69.23. My population standard deviation, I have highlighted in green. It says assume the population standard deviation of $3.72. If I back up to the second sentence, it says to test the claim, a researcher selects a sample of 30 hotel rooms. So my sample size is 30 and finds the average cost for those 30 is $68.43. And then in the last sentence, it tells me at a 0.05 significance level. Now for Minitab, it prefers you to have the confidence level. If alpha is 0.05, my confidence level is 95%. Remember, those two values have to add to 1. Okay, so I have all of the information that I need from the problem. So I'm going out to Minitab and I'm going to conduct my one mean z-test. We go to Stat, Basic Statistics, one sample z. We have summarized data. My sample size was 30 hotel rooms. The sample mean was $68.43. The given population standard deviation, which is known, is $3.72. I'm sorry, I've got the yawns today. We are performing a hypothesis test, and my hypothesized mean is the $69.23. Select options. We are using 95% confidence level, and my alternative hypothesis contains not equal. So I click OK. I click OK again, and I get under the header test, it gives me my z value. My z value here is negative 1.18, and the corresponding p-value is 0.239. So I'm going to copy those answers over to my paper. Okay, so my test statistic from Minitab, the z is negative 1.18. The corresponding p-value is 0.239. I then have to make my decision. I make the decision by comparing the p-value that we just got from Minitab to the alpha that was given in the problem. So my p-value is 0.239. Alpha is given as 0.05. When you compare that digit for digit, you have 2 compared to 0. 2 is greater than 0, so P is greater than alpha. When P is greater than alpha, we fail to reject the null. If we fail to reject the null, that means the null is true and the alternative is false. So when I write my conclusion, we write it in terms of the true statement. So we would say, at the 0.05 level of significance, the average mean cost of a hotel room in Atlanta is $69.23. Again, I think it's easier to work through the entire problem on my paper and then go back into D2L and answer the questions. All right, let's move on to scenario 3. Scenario 3 says a researcher reads that the marital status of U.S. adults is distributed as follows. Never married, 30%. Married is 56%. Widowed is 3%. And divorced is 11%. He selects a sample of 400 people, and the results are shown below. At the 0.05 level of significance, can it be concluded that the marital status of U.S. adults is as she read or as stated? So again, you got to recognize what type problem this is. I noticed that my responses are words: never married, married, divorced, and widowed. And we want to compare those. And so this is a chi-square goodness of fit. We're given the categories and the observed number from our sample of 400. We also have given to us in the problem specific proportions or percentages for each category. So again, we begin each hypothesis test the same way by stating our null and our alternative hypothesis. We typically use words here, so we would say the data follow the stated distribution. And then we list that out. We would say never married, 30%, married, 56%, widowed, 3%, and divorced, 11%. Okay, again, remember the null has to imply that it's equal or the same. The alternative would be the data do not follow the stated distribution. And again, you could write it out. I'm not going to for time's sake. And then we need to find our test statistic and corresponding p-value. In Minitab, which I went ahead and typed it in to save some time, you have to type in this information. So for chi-square goodness of fit, we would, let's see, got to find the right data set here. Let's get this out of the way. Okay. Let's see. is here somewhere. I had it earlier. Okay, well, we can retype it in. So you would have their status, which is never married, married, widowed, and divorced. You would enter the observed, which is what's given to you in the table. And we had 150 never married, 228 married, 5 widowed, and 17 divorced. You also have to tell Minitab the expected percentages. And again, those are given to us. We had 30% for never married, written as a decimal is 0.3, 56% married, 3% widowed, and 11% as your divorced. Okay, so then we're going to calculate our chi-square. We go to stat, tables, chi-square, goodness of fit. Our observed counts are in column 2. The category was in column 1. We are doing specific proportions from historical counts, and those are in column 3. That's our expected. And then we click OK. And again, Minitab always really gives us more information than we need. If you need the expected, based on the percentages that we gave it, we would have expected 120 people to never marry, 224 to be married, 12 widowed, and 44 divorced. Okay, so Minitab does calculate our expected based on the percentages that we gave it for the 400 people in the survey. We keep scrolling until we get to chi-square test, and we get our test statistic, which is 28.2229, and our p-value is 0. Okay, so we go back and we write that down. Our test statistic, which is chi-square goodness of fit, is 28.2229. The corresponding p-value is 0. We then compare the p-value to the given alpha, which is 0.05. So we're going to compare 0 to alpha, which is 0.05. Again, I'm going to do that digit for digit, 0 to 0, 0 to 5. 0 is less than 5, so P is less than or equal to alpha. When P is less than or equal to alpha, we reject the null. If we reject the null, that means the null is false, and then the alternative is true. So in this scenario, what that means is it means at the 0.05 level of significance, the data do not follow the stated distribution, which again, the stated distribution is never married 30%, married 56%, widowed 3%, and divorced 11%. And you could list that out. in your conclusion. But the key thing is to realize that it does not follow the distribution. Okay, moving on. Scenario 4, again, if I read through it, we got to recognize what kind we're going to have. It says, suppose a group is interested in determining whether teenagers obtain their driver's license at approximately the same average age across the country. Suppose that the following data are randomly collected from 5 teenagers. It really should be 4 teenagers because I only have 4. Okay, so there's a typo there. This should be 4. 4 teenagers in each region of the country. The numbers represent the age at which teenagers obtain their driver's license. Use a level of significance of 0.10. And I notice that I have northeast, south, west, and east. So I have the ages, which is my variable, and they're sorted into categories by region of the country. So this represents an Anova, an analysis of variance. I have numbers sorted into categories. So we would have our null and our alternative hypothesis. And there's different ways to do this. We usually write it in words, and we would say the mean age at which teenagers obtain their driver's license is the same across the country. We're basically saying that the average age for the Northeast is the same as the average age for the South, is the same as the average age for the West, is the same as the average age for the East. The idea is that they're the same, which implies equal. The alternative would be that they're not the same. The mean age at which teenagers are playing their driver's license is not the same across the country. Okay, so again, our null has to imply equal, and the alternative is going to imply not equal. We then have to enter the data into Minitab to get our test statistic for Anova, which is the F, and our corresponding p-value. So I have already entered the data, and when you enter the data, you do have to enter it and keep it sorted. So you have a column for Northeast, a column for South, a column for West, a column for East. And we go to Stat, Anova. We're doing one way. My data is in separate columns, and then I have to choose all the columns where the data is located. So I have 4 categories: North, East, South, West, and East. So I choose all 4, and I click OK. Again, it gives us the method. It does give us the hypothesis, all means are equal or not all means are equal, in case you kind of forget, it is there. And we go down to the analysis of variance. We get our F value, which is 2.40, and our P value is 0.118. Okay, so we go back over and we write that down. Our F test statistic is 2.40. The corresponding P is 0.118. Again, we're going to compare as we always do, we compare P to alpha. Okay, so we're going to compare the p-value, which is 0.118, to the alpha, where they told us to use 0.10. So I'm going to make that comparison. 1 compared to 1, that's the same. 1 compared to 0. 1 is greater than 0, so P is greater than alpha. If P is greater than alpha, then we fail to reject the null. If we fail to reject the null, that means the null is true and the alternative is false. So in this case, the mean age at which teenagers obtain their driver's license is the same across the country. Okay? So we would write at the 0.10 level of significance, the average age at which teenagers obtain their driver's license is the same across the country. Okay, moving on to scenario 5. The data below gives the gold medal times for every other Summer Olympics for the women's 100-meter freestyle swimming. Can you predict the gold medal times by the year? Although we did talk about several different ones where you had perhaps two variables, this is probably the only one where we really truly had two different variables. You have both the year and the time, and we're looking for a connection, a relationship between that data. And so this particular question gets us into correlation and regression. And so initially we have to identify the independent variable, which represents the x, and we have to identify the dependent variable, which represents the y. And a lot of you had trouble with this. But guys, there's a standard across the board so that regardless of whether you're sitting in Georgia or England or France or Germany, you read it the same way. Typically, the left-hand column, or if it's in rows, the top row of a table is going to represent your independent. That is the year. The independent is the variable that you as an individual can choose or can manipulate. Similarly, then, the dependent is in the right column or the bottom row. So in this case, that would be the time in seconds. Now from there, in the D2L and your homework and quiz and stuff, it kind of goes off on a little tangent for a little bit. and assumes you've created the model and all that kind of stuff. So I'm going to walk it through like you were doing it paper and pencil. So then I want to take a look at the scatter plot of this data, and hopefully then there's going to be a pattern within the dots. So we enter the data, keeping them paired together as they're given to us into Minitab, which I've already done, okay? And one of the things that I do to help me out so that I don't get confused as I'm working through the problem is I have the year and I labeled it as the X, and I have the time and I have that one labeled as Y. Okay? Let's spread this out where you can see it. So then I want to look at a scatter plot, and there's several ways to get the scatter plot. The easiest is to go to Stat, Basic Statistics, and then we scroll down to the option Correlation. And I'm going to indicate the two variables that I'm interested in. I'm interested in year and time. And I click OK. And I like this method of finding the scatter plot because it's going to give me some additional information. Okay, so I don't know if I'll be able to get this where you can see all of it. Okay, but it gives you a picture of the ordered pairs. Okay, so it looks like as the years go up, the time goes down. So we look at the graph, and again, it's hard to see the whole thing at one time. There does appear to be a pattern. That pattern appears to be linear, and it appears to be negative. The other thing that I like about this command in Minitab is it goes ahead and gives you the correlation coefficient. So one of the next questions you get in Minitab is what is the sample linear correlation coefficient, which is R. And R is a measurement of the strength and the direction of your relationship. And so if you go back and look, we found that R was negative 0.904. Now, a couple of things real quick. I know this video is going to be long. Is the R value is between -1 and +1. The closer you are to 1 or to -1, the stronger the relationship. Some rules of thumb that you can use is I tend to use 0.3 and 0.7. In between 0 and 0.3, we say it's weak. Between 0.3 and 0.7, it's moderate. And then 0.7 to 1 is considered strong. So my gut tells me that R equals negative 0.904, that I have a strong negative linear correlation. But again, that's kind of my gut, my eyeballs, just what I think, my interpretation. We don't get to leave it at that point. We have to verify, we have to prove that it is an actual strong negative linear correlation. So we run a hypothesis test. Our hypotheses, we say rho equals 0. This is the Greek letter rho, and it represents the population linear correlation coefficient. Now, for rho to be equal to 0, to think about what that means there is not a linear correlation and R, which is your sample linear correlation coefficient, is not statistically significant. The alternative is that rho does not equal 0. Again, rho is your population linear correlation coefficient. For it to not equal 0 means there is a linear correlation and R is statistically significant. So then we have to go out and run our hypothesis test and get our test statistic and our corresponding p-value. So I'm going out. Again, I have the data already entered for correlation and regression. We go to stat, regression, regression, fit regression model. My response is always the Y. My continuous predictor is always the X. And then I tell it, okay. Now I get lots of information, but I'm looking for my test statistic and p-value. So I'm going to scroll down to the header, analysis of variance. And I find that my F test statistic is 17.96 and my corresponding p-value is 0.013. Now, I really don't need to record the F value. I'm not asked for that in the questions. I am asked for the p-value. So my p-value is 0.013. And again, I'm going to compare that p-value from Minitab of 0.013 to the significance level. And for this problem, let's see, what did it tell me? It didn't. So typically, if we're not told, we assume it is 0.05. We then begin making the comparison 0 to 0, 1 to 5. 1 is less than 5. P is less than alpha or equal. Since P is less than or equal to alpha, we reject the null. So if we reject the null, that means that our null is false and the alternative is true. So because we reject the null, then R is statistically significant and there is a linear correlation. So we have now proven beyond a shadow of a doubt there is a relationship or a correlation between the year and the time in seconds. That means we can then create the model or that line of best fit for the data that we're given and then use it to make predictions. So we need the line of best fit. Again, this is your model. We already found that in Minitab. You may not have realized it when we did stat, regression, fit regression model under the header regression equation. It gives me the model. Now I need to put that in terms of X and Y and math symbols. So I would have Y equals 349.0 minus 0.1476x. Let me make sure I wrote that down and remembered it right. 349.1476. Okay. Now, in that model, and this is something that a lot of you are also getting confused about, in this model, the number that's out here first without the x variable is your y-intercept. Then the number with the x, including the sign, is your slope. Okay, so think this is like y equals b plus mx rather than your traditional mx plus b. So that gives you your y-intercept and your slope. I point that out because I know that the test asks you specifically for the slope and the y-intercept. The slope is always the one that's not paired with the x, and the slope is the one paired with the x. Once you have the model, you can then create or make a prediction. And you have to be given a value. And let me see if I can go out to the test itself and find the value that it asks you to do. Okay, so under scenario 5, question 36 says, if you can make predictions when the year is 1988, the gold medal time would be. So they're giving me the year of 1988. Okay, so they tell me that the year, which is X, is 1988. I am simply going to plug and chug that into the formula. So I would have y equals 349.0 minus 0.1476 times the year of 1988. You want to get your handheld calculator and perform those calculations. So if I do that, I have 349.0 minus 0.1476 times 1988. And I have 55.5712. It does ask you to round to one decimal place, so it rounds to 55.6 seconds. And then it asks you for the r squared value, which is your coefficient of determination. The coefficient of determination is going to help you to make a decision about whether or not should you really even use the year to predict the time to complete the 100-meter freestyle. Okay, so it is written as a percentage, and again, it's given to us after doing the command stat, regression, fit regression model. I scroll to the header model summary, and it gives me R-SQ. So R squared for this problem is 81.79%. 81.79%. So R squared equals 81.79%. So we would say approximately 81.79% of the variation in the time can be determined by the variation in the year. Now, a couple of things about writing that conclusion. In that conclusion, guys, you got to have the word variation. I have it capitalized. And it's always the variation in the time, which is y, can be determined by the variation in the year, which is x. Y is first and then x. And your value for r squared will change from problem to problem. Okay, this video is getting rather lengthy, and we have 5 more problems to do. So I'm going to stop here and let this be part 1, and then I'll create a second video to go through the other problems for you.